Okay, I'll get started. Just wanted to begin with a Test 2 announcement. So Test 2 scores are in the grade center. You should see your Test 2 score there. Test 2 exams were passed back in recitation yesterday, so you should have your exam back. I have a few, if you took your exam with the DRC. The average on Test 2 was 79%. That's actually great. That's the highest Test 2 average I've ever had. So that's fantastic. The distribution of Test 2 scores is posted here and posted on Canvas. I will post the solutions to Test 2 when we've got all the makeups done. And we won't get all the makeups done till the end of the week. So that's gonna take one more week. If you've got any queries, questions with the grading on Test 2, you can see me, see your recitation instructor. Let's get that wrapped up by 1 week from yesterday, so next Monday. Any questions on the Test 2 scores, grading, etc., etc.? Okay, no questions on Test 2, so I'll move on to today's content and the course content for the rest of the semester. We're moving on from electricity, magnetism, and electromagnetism to light and matter and space and time. We're going to cover all that in about, 5 weeks or something like that. We're going to start with light. We're going to begin with light, but work our way through light, matter, space, time. So the amazing thing to me about light is how, from a basic dimension property of nature, how from the dimension of nature of positive and negative charges emerged light, a bundle, self-propagating bundle of electromagnetic waves that emerged from there being positive and negative charges in matter. We're going to explore the properties of light, the characteristic of light. We'll see that there's a whole range of properties of light. There's refraction and reflection, we'll say what those are. There's interference and diffraction, we'll say what those are. We'll talk about the speed of light. So we're going to spend some classes exploring all the properties of light, this thing that emerged from electrical charge. All these properties that emerge from electrical charge of light, light reflection, light refraction, light interference, light diffraction, can all be traced down to the electromagnetic nature of light. And sometimes we'll trace them down to the electromagnetic nature of light, and sometimes you'll just see the laws that emerge from the electromagnetic nature of light. Anyway, that's the plan. As we talk about light, we'll actually talk about light from a perspective where light is both a wave, so the wave nature of light, but also a perspective of light where it acts as a particle nature of light. Now, in reality, light is actually, it's not simply a wave, it's not simply a particle, i.e. it's not a wave or a particle, but rather it's something else that exhibits both wave-like and particle-like properties. So as we talk about light over the next handful of classes, we'll be meeting both wave-like properties and particle-like properties of light. And it's just one of the very strange, peculiar things about light, that it possesses both wave and particle-like properties. Here's just a little history little spoiler on wave light and particle light properties of light. So Newton originally, Isaac Newton, we all know Isaac Newton, he originally thought of light as a stream of particles. And he was able to explain a reflection of light as a stream of particles. Another very famous scientist at the time, Huygens, Christian Huygens, he thought of light as a wave, and he was able to explain effects of light, like light traveling through a pinhole, through it being a wave. Later on, it was established in experiments, firstly, that light is a wave by observing interference, and then later on, not much later on, it was established that light is a particle by watching light collide with electrons. So experiments later came that proved that, firstly, that light was a wave, and then proved that light was a particle. And the only resolution we have of that is due to Einstein, is that light is neither a wave nor a particle. It's something that possesses both particle light and wave light properties. And actually those particle light and wave light properties are related to one another by a very famous equation. It's Planck's equation. I wrote it down here right at the bottom. It's that the energy of light particles, so that's the E in Planck's equation, is related to the frequency of light waves, that's the F in Planck's equation. By Planck's equation, E equals HF, so in that equation, E on the left-hand side is particle light properties, F on the right-hand side is the wave light properties, and E equals HF, where H is just a constant of nature. It's just a constant of nature, that we would measure this constant of nature, and that constant of nature, because it's called Planck's equation, is called Planck's constant, and it has some number. It's some number that's tiny in units of joules, which are on the right-hand side, and seconds, which are on, joules are on the left-hand side for the energy, and frequency, or time, that's on the right-hand side, seconds, is some number that's this number here, 6.6 times 10 to the minus 34 joules seconds. And so that little equation and that little constant of nature link the wave light and particle light properties of light, which are a very, very strange feature of light. That it's not simply a wave, it's not simply a particle, it's something beyond that, different from that, that exhibits both wave light and particle light properties. Okay. As I said, that was kind of a spoiler for the next few classes, the next handful of classes, where we're going to go through both particle-like and wave-like properties. Today's class, finally got to today's content after about 15 minutes. Today's content is this list of bullets here. So we're going to talk about three things, basically: propagation of light, we're going to talk about reflection of light, we're going to talk about refraction of light. We're going to talk about law of propagation of light, law of reflection of light, and law of refraction of light rays. And we're going to talk about, obviously, what propagation, reflection, refraction actually are, and we're going to look at examples of reflection, refraction, and propagation of light. So we're going to do all those things. To do all that, the first bullet says, I want to first introduce the idea of rays of light, light rays. I want to introduce ray tracing, tracing of light rays, and I want to introduce the ray approximation that we'll be using today. So that's the first topic. That'll lead us into propagation, reflection, refraction of light. The first topic is just one slide. Here it is. You know, we're used to in our everyday language talking about rays of electromagnetic radiation. So we talk about X-rays. You know, if we go to the hospital because we broke our wrist, we'll talk about X-rays. We talk about gamma rays. Gamma rays are also available in hospitals for diagnostics. We talk about light rays, rays of sunshine. So we talk about rays of electromagnetic radiation. But what do we mean by rays of electromagnetic radiation? Well, I try to picture it on this slide. Here I'm picturing in blue some rays of electromagnetic radiation. These rays of electromagnetic radiation, they might be gamma rays, they might be X-rays, they might be regular old light rays, or some other electromagnetic rays. These rays of electromagnetic radiation are traveling from the left of the screen to the right of the screen, and the direction of the rays, which is pointing from left to right, tells you the direction of propagation of the light wave or the gamma ray or the X-ray or whatever wave it is. They also tell you the direction of flow of the energy in the electromagnetic wave, so in the light wave or the gamma ray or in the X-ray, and they tell you the momentum direction that's carried, the momentum flow that's carried by the light ray or the X-ray or the gamma ray. Now, this idea of picturing electromagnetic waves as rays that travel, say, from the left to the right and carry energy momentum from the left to right is valid in some circumstances and not valid in other circumstances. So I want to explain what circumstances our rays are valid in, which is what we're going to be working on today, what circumstances they're not valid in, which is something we'll be working on in later lectures. So this ray approximation, picturing the light as rays, is good, is valid, is appropriate when your light rays interact with things that have dimensions, have size, that are much, much bigger than the dimensions or size of the waves, the wavelength of the light or gamma rays or X-rays themselves. So in picturing light interacting with things, so light, say, interacting with a lens, or light interacting with a mirror, or light passing through a pinhole, there's two dimensions that are relevant to light traveling through a lens, or light traveling, striking a mirror, or light passing through a pinhole. The two dimensions are the wavelength of the light itself and the dimensions of the lens or the mirror or the pinhole. And the ray approximation, this ray tracing, is appropriate if the wavelength of the light or the electromagnetic radiation is much, much smaller than the size, dimensions of the mirror or the lens or the pinhole. So if you think about if you think about visible light, so visible light has wavelengths that is from 400 nanometers, that's the shortest, that's 400 times 10 to the minus 9 meters, to 700 nanometers, that's 7 times 10 to the minus 9, 700 times 10 to the minus 9 meters. So that's the wavelength of visible light. The dimensions of a lens or a mirror, say in a microscope, or in a telescope, those dimensions might be centimeters or tens of centimeters. So the dimensions of the lens or the mirror in a telescope or a microscope is much, much bigger than the wavelength of the light itself, which is just 400 to 700 nanometers for visible light. So that's a case where the dimensions of the lens and the mirror are much bigger than the size of the wavelengths of the light, and so ray tracing is a great approximation there. We can use it, we can go ahead with it, it's perfectly valid, perfectly reasonable. For radio waves have wavelengths that are many meters and even kilometers. So if radio waves are interacting with something that has dimensions of centimeters or tens of centimeters or whatever, then ray tracing is a very bad approximation for radio waves. So radio waves are an example of a type of wave that has a very long wavelength. We don't very often think about radio waves and ray tracing because ray tracing is not a good approximation, not valid for radio waves. Okay. So I'm going to, over the next few slides, introduce three laws. The law of propagation of light rays, law of reflection of light rays, law of refraction, we'll say what refraction is, of light rays. These laws, I should say, emerge from, they are consequences of the fact that light is a bundle of electric and magnetic fields, self-sustaining, self-propagating electric and magnetic field bundle. And the laws of propagation and reflection and refraction emerge from that understanding of the electromagnetic nature of light and the electromagnetic nature of matter. We're not going to prove the laws emerge from the electromagnetic nature of light and matter. Rather, we're going to just write down the laws for propagation, reflection, and refraction. Now, in one case, I would say you'll just think, well, this law is obvious. Why did you make such a law out of it? It's so obvious, you don't need to make it a law. In another case, you're probably going to think, where on earth did that law come from? How did that law appear? But both of them, all of them, do come out of the electromagnetic nature of light and matter. Okay. So this is the one, this is the law that's completely obvious. Why am I making it a law? It's the law of propagation of light. When light travels from some point, I labeled it P, to some other point, I labeled it Q, it travels from P to Q in a straight line. That's the law of propagation of light. It's as simple, straightforward as that. And I pictured it here. And this is a very old discovery. This is a very ancient discovery, thousands of years old. The ancient Greeks and ancient Egyptians knew that light propagated in a straight line. Now, to be fair, light actually doesn't always propagate in a straight line. Sometimes it propagates in a curved line. It propagates in a straight line if the material through which it's propagating, the matter through which it's propagating, say the atmosphere or say the ocean, is uniform, optically uniform. If that matter, the atmosphere, is not optically uniform, or that ocean is not optically uniform, then light will propagate in not a straight line, in a curved path. So the law of propagation of light in a straight line applies to propagating through a uniform material, the uniform atmosphere or the uniform ocean or any other uniform material, like a slab of glass or a slab of clear plastic. Okay, that's one law down. Law of reflection. We all know what reflection is. It's when light bounces off a material. That's reflection. We know reflection from light bouncing off a pane of glass or light bouncing off a mirror in the bathroom. So those are all examples of reflection. The law of reflection was also discovered thousands of years ago by the ancient Egyptians and the ancient Greeks and so on, ancient Babylonians. And the law of reflection also seems like a kind of simple and straightforward and obvious law. I pictured the law of reflection here. In this picture, imagine you got two different materials. So let's imagine upstairs here, above the horizontal line, is air. And let's imagine downstairs here, below the horizontal line, is water. And so there's a boundary between the air above the horizontal line and the water below the horizontal line. And this is that boundary. And what I'm sketching is a light ray approaching that boundary from the air towards the water and being reflected, bouncing off the air-water boundary. So here comes in the light ray from point P. This is a ray. I'm ray tracing, so that's why I introduced ray tracing. That's the incident ray. Here's the reflected ray, the bounced off ray. That's the outgoing ray. Again, this arrow is a ray. I'm ray tracing, and it's heading towards this point Q. And the law of reflection says that the incident angle of the light ray, so we call that theta subscript I for incident, is simply equal to the reflected angle, and we call that theta subscript R for reflection. And so I pictured that here. Notice, important point here, when we measure the incident angle, reflected angle, when we quantify incident angle and reflected angle, we measure them not with respect to the boundary itself, the horizontal line. Rather, we measure them with respect to a right angle, a normal, with respect to the boundary itself. So theta I is measured from this normal line here, this vertical line here. And theta R is measured away from this vertical line, this normal line here. So that's how we define the theta I and theta R. And so this is a law of reflection. In a way, this is obvious too. If you imagine like ping pong balls striking a wall, right? They obey the law of reflection. The angle that they strike the wall at with respect to the normal is the angle they bounce off the wall at with respect to the normal. So this law, I think, also is kind of a common sense law about the reflection of light, especially if you think of light as a stream of particles, like a stream of ping pong balls striking the mirror and bouncing off the mirror, or striking the water, bouncing off the water. I should say that just like the law of propagation, there are exceptions to the law of propagation when the material is not uniform. The law of reflection, there are exceptions to the law of reflection when the material, the boundary is not smooth and uniform. Maybe when it's rough and irregular. So when the boundary is smooth and uniform, like a pane of glass or like a mirror, bathroom mirror, that's called specular reflection, and the law of reflection applies to that. When the surface that the light is striking is rough and irregular, that's called diffuse reflection, and the law of reflection doesn't apply to that. Let me just show you an example of that. So here's two examples. The one on the left is the specular reflection, where the law of reflection applies. The one on the right is the diffuse reflection, where the law of reflection doesn't apply. In both cases, there's the car or the van headlights that are the source of the light. So this is where the light ray is coming from. Over here on the right, this is where the light ray is coming from, the van headlights or the car headlights. The light is being reflected, some of the light is being reflected off the surface of the road. So there's light reflection off this surface of the road downstairs here on the left, light reflection off this surface on the road over here on the right. This road is damp, wet, and it's a relatively smooth surface. This road is dry, not wet, and so it's a relatively rough, irregular surface. You get more like specular reflection off this surface here, and so we see more clearly the reflected lamps, headlights of the car or the van. You get diffuse reflection here. You see less clearly the headlamps or the lights of the van or the car in the road surface here. And so these are just comparing what are approximately specular reflection over on the left-hand side with the wet road surface, a smooth surface, approximately diffuse reflection on the right-hand side with an irregular dry road surface. Okay, last law, law of refraction. Refraction, maybe not everybody knows what refraction is, but so let me explain what refraction is. Everybody knew what reflection is and what propagation is, but not everybody knows what refraction is. It's the bending. It's the deflection of light when it travels from one material to another material. That's all refraction is, fancy word for that. So if light travels from air to water, then in general the light ray is bent as it travels from air to water, and that's called refraction. If light travels from water to air, the other direction, then in general that light ray is deflected as it travels from water to air. And that's called refraction. If light travels from air to glass or glass to air, that also involves refraction, bending of the light rays. So it's a law of refraction is a law about how much the light rays get deflected or bent when they travel from one material to another material, and those materials could be air, water, glass, ice, and so forth. So here's a picture of refraction, and then here is the law of refraction. And let me say that whilst the law of propagation of light rays is ancient, and the law of reflection of light rays is ancient meaning that they were, those laws are identified thousands of years ago. Law of refraction is much more modern. It's only a few hundred years that we've known the law of refraction. It's, in a sense, it's a very interesting and curious and maybe mysterious law. So we'll see what it is. So in the picture here, I'm imagining two different materials separated by this horizontal line, this boundary here. Upstairs might be air again, and downstairs might be water again. So imagine that sort of situation. Again, we're imagining a light ray that's approaching the boundary from upstairs here, from this point P, and then it strikes the boundary, and this time it's travels into the other medium. It's not reflected, it's refracted. It travels into the other medium, and here it is heading away. So this arrow upstairs here on the left, this is just an example of a ray and ray tracing. It's the incident ray. This arrow's downstairs here on the right, another example of ray, ray tracing. It's just the outgoing or refracted ray. And you can see here, I've anticipated the bending, refraction, deflection of the light ray because I drew the directions of the approaching ray and the receding ray as different. The light ray was bent, was refracted. We can quantify that refraction or that bending of the light rays by defining the incident angle, theta I, the refracted angle, theta r. So here we're using theta I and theta r for incident and refracted. Before we used theta I, theta r for incident and reflected, but we've got the same subscripts. Again, we're measuring with respect to the normal. That's how we define these angles. And again, you see here, in refraction, you see that theta I in this particular case is larger, theta r in this particular case is smaller. How are those two angles related to one another? That was a mystery for thousands of years. Nobody knew how they were related to one another until Snell, scientist Snell. We've got to thank him for the law. It's called Snell's law, and this is the relationship between the two angles, theta I and theta r. So here's sine theta I, sine of the incident angle. Here's sine theta r, sine of the reflected angle. The other thing you see in here is an Ni and an Nr. What are these two numbers? These are just numbers. That's the first thing. They don't have units, so they are just numbers. Ni is a number. Nr is a number. Those two numbers characterize the optical properties, optical nature of the two materials, the air from which the light approached and the water from which the light traveled into. So whenever you have a boundary between two materials, you've got two different materials, you've got two different optical materials, might be air and water, might be air and glass, might be glass and water. And each of those materials has a characteristic refractive index that we give the symbol N. And that refractive index is key to determining the two refractive indices of the two materials, is key to determining the deflection, the refraction of the light ray at the boundary between the two different materials. And so that's all embedded in Snell's law. And I don't know, at this point I was always thinking, when I first found out about Snell's law, for some reason I remember there's a why. You know, why is it that Ni sine theta I is equal to Nr sine theta r? Why is there that relationship between the incident and reflected angles and these two characteristics, the Ni, the Nr of the two different optical materials? The only explanation I can give you, without a lot of mathematics, is that this law, this simple little law, Ni sine theta I equals Nr sine theta r, actually emerges from understanding that light is an electromagnetic wave, matter is an electromagnetic environment, it has electromagnetic properties, and the interaction between the electromagnetic wave and the electromagnetic properties of matter generate Snell's law. It's fantastic. So it's not a mystery. Snell's law is not a mystery. It's not a controversy, but it literally emerge from our understanding that matter is electromagnetic and light is electromagnetic. And using that understanding, you can predict Snell's law. Snell's law is really kind of an emergent equation from our deeper understanding of the electromagnetic nature of light and matter. Okay. You notice on here that when I said this was going from air to water. When you go, and air has a small refractive index, and water has a larger refractive index. When you go towards larger refractive index, you're bent towards the normal. If we went from water to air, which would be going the opposite direction, that would be going from larger refractive index to smaller refractive index, you're bent away from the normal. That is all embedded in Snell's law, that if the incident refractive index is smaller, then you're bent towards the normal. If the incident refractive index is larger, you're bent away from the normal. So it's all embedded in Snell's law, but it's a key feature of Snell's law, whether you're bent towards or away the normal, the direction of the refraction, the direction of the reflection. Okay, here's just a list, this is stolen from the text for, a long list of refractive indices of different materials. So you can just walk off and measure refractive indices of different materials, and once you know these refractive indices of different materials, you can predict the bending of light rays as light travels between one material and another material at whatever angle that it strikes the boundary between the two materials. So armed with the refractive indices, you can calculate the refractant for any light rays in any directions between any pairs of materials. So that's the power, that's the huge power of Snell's law. Just to point out a couple of things, water and ice, they both have the refractive indices about 1.33. Water is slightly larger, ice is slightly smaller. Air, on the other hand, that has a refractive index that's almost 1. It's just fractionally, part in 10 to the 4, greater than 1. So here's air. Vacuum, doesn't list vacuum here, but that empty space has a refractive index of 1. So having no electromagnetic effect, having no electromagnetic matter, means you've got a refractive index of 1. Having some electromagnetic effect, like having air present, which is electromagnetic, or water or ice present, means you've got a refractive index greater than 1. One really big, famous refractive index is diamond. If you've got a diamond ring, I'm imagining the Queen now, but she's dead. But I still imagining her with these big rings. They sparkle so much because they have such a high refractive index. Diamond has such a huge refractive index. Light goes in it, and because of the refractive index, it actually gets trapped inside the material and then comes out in all different directions and gives a fantastic sparkle of diamond. So that's why that's why diamond has that characteristic sparkle, because of its very high, unusually high refractive index. Okay, here's just a few details about what changes, what doesn't change when light travels from one material to another material. So here's a picture of light traveling from one material to another material, from the upstairs material refractive index N1 to the downstairs material refractive index N2. To keep this figure simple, I just imagine that the light is approaching at 0 degrees to the normal, so vertically downwards to this boundary. And actually Snell's law then tells you that the light emerges at 0 degrees to the normal. So that's a special case in Snell's law. If you approach at 0 degrees, you actually emerge at 0 degrees. You're actually not deflected when you strike a boundary at right angles to the boundary. Special case of Snell's law. Anyway, that's what's happening here. What happens to the speed of the light ray as it travels from one medium to another medium? What happens to the wavelength of the light ray as it travels from one medium to another medium? And what happens to the frequency of the light ray as it travels from one medium to another medium? So if I think about a light wave or electromagnetic wave, I can think about, well, how fast does it travel, its speed. I can think about its wavelength, the distance between successive crests or troughs of the wave, and I can think about the frequency, the time between crests and troughs, or the number of crests and troughs per unit time. So I can think about all those things about an electromagnetic wave. How do they change, or do they not change, when light travels from one medium to another medium? This slide is just a list of how they change. Let's start with the speed. So one thing that's really interesting is we said that light has a speed of 3 times 10 to the 8 meters per second. This was Maxwell's, James Clerk Maxwell's great, famous moment prediction that light travels with a speed of 3 times 10 to the 8 meters per second. But that's the speed of light in pure vacuum, in empty space. In material, like in air, for example, or in water, for example, or in glass, for example, light actually travels slower. And the factor by which it travels slower in air or water or glass is the refractive index, this optical property of every material. So in air, light doesn't travel quite at 3 times 10 to the 8 meters per second. It travels a factor, if you remember the number, the refractive index of air was, I think it was 1.00023 or something like that, or 29. It travels that factor slower in air. So tiny, tiny bit slower, but barely slower. In water, right? If light's traveling in water, it doesn't travel at 3 times 10 to the 8 meters per second. It travels slower by a factor that's a refractive index. The refractive index of water was 1.33. So it's actually slowed significantly in water. It's a little bit more, its speed is a little bit more than 2 times 10 to the 8 meters per second. So quite a bit less than 3 times 10 to the 8 meters per second. And in diamond, for example, where the refractive index was 2.5 or something, then light travels that factor slower in diamond, much, much slower in diamond. So light travels slower in different materials in proportion to the refractive index of those materials. So that's an important comment here, and I wrote it down in this way here, that the speed of the light ray in material number 1 is the speed of light in vacuum, that's C, divided by refractive index in material 1. The speed of light in material number 2 is the speed of light in vacuum divided by material 2's refractive index. What about the wavelength? What about the wavelength of the light? That's also really interesting. So the wavelength of the light is also changed when light travels from one material to another material, just like the speed changes from one material to another material. The wavelength of light in a material is shorter than the wavelength of light in vacuum, again by this factor of the refractive index. So in air, compared to vacuum, a light ray's wavelength is a tiny, tiny, tiny bit shorter by this factor, the refractive index of air, which was 1.00029. In water, the wavelength of a light ray in water is shorter than its corresponding wavelength in vacuum by a factor of the refractive index, which was 1.33. So it's significantly shorter. And then in diamond, right, refractive index of more than 2.5, the refractive index of the wavelength of a light ray is much shorter, 2.5 times shorter than the wavelength, the corresponding wavelength of the light ray in vacuum. So the wavelengths are shortened, just like the speed is reduced according to the refractive index of the material. The thing that doesn't change, though, is the frequency. So what's interesting is that the frequency of the oscillations, the number of oscillations per second of a light wave, or the time between successive oscillations of a light wave, that's the same whether that light ray is traveling through vacuum or air or water or glass. So frequencies are unchanged. So although the speeds slow down, although the wavelength's shorter, the frequencies are the same. And it actually has to be that way to obey that relationship between speed, wavelength, and frequency, that the speed of the wave is the product of the wavelength of the wave and the frequency of the wave. Okay. Again, all of this, I'm just telling you, right? I'm just telling you and asking you to believe me that the speed of a light ray in a material is slower, that the wavelength of light in a material compared to vacuum is shorter, but the frequency is the same of the light wave in a material and in vacuum. I'm just asking you to believe me that. But actually, based on the fact that we know that light is an electromagnetic wave, the bundle of electric and magnetic fields, and matter is an arrangement of electrical charges and currents, it's electromagnetic, you can predict the relationships between the the speed and the wavelength and the frequency of the light wave and the refractive index as the materials is traveling through, and you get these predictions. So this is understood. What I just told you as a rule is understood in terms of electromagnetic theory and the fact that light and matter are electromagnetic. So we understand it all. Okay. I want to show you a quick video just to demonstrate refraction, I think. This picture, let me just, I'm not going to do this demonstration because I'm totally panicked about time. And I want to get on to some examples. But this picture here shows you both, well, both, I think both's not the right word. It shows you propagation, the law of propagation, shows you law of reflection, and shows you law of refraction. The three laws we just discussed, all in one simple picture. It's fantastic. I like it for that reason. Here comes an incident light ray. That's ray number one. And it's traveling in a straight line. So it's obeying the law of propagation. So there's the law of propagation here, this incident light ray. It strikes this boundary. This is a boundary between air and some piece of plastic. Transparent plastic. At that boundary, some of the light ray is reflected and some of the light ray is refracted. Some bounces off and some heads into the material that it strikes. The light ray number two, that's obeying the law of reflection. The angle of the light ray number two with respect to the normal equals the angle of light ray number one with respect to the normal. So these two rays obey the law of reflection. Theta I equals theta R. And then look at this refracted ray down here. It's deflected. It's bent away from the original direction. It's actually bent towards the normal. Theta refracted is smaller. Theta incident is larger. This is obeying the law of refraction. This is obeying Snell's law that Ni sine theta I equals Nr sine theta R. And so here we see the law of refraction. And so all those laws of reflection, refraction, and propagation are on this picture here. Let me show you one more example in a little video. So in this picture, here's the incident ray, here's the refracted ray, here's the atmosphere, and here's water as the two materials with the two refractive indices. Refractive index of water is 1, refractive index of air is 1, and water is 1.33. Here you see the refraction of the light ray is being bent as it moves from the atmosphere into the water. That amount of bending depends on the incident angle according to Snell's law. And we said if we approach at 0 degrees, we are not bent, we're not refracted. And so here you see 0 degrees in, 0 degrees out. Now as we increase the angle, we're increasing the bending. All of this is in accord with, in agreement with Snell's law of prediction. And so this is, you're seeing in this this is a video of Snell's law. This is a video of Snell's law versus theta I, incident angle, for two different examples of refractive indices. Air, 1.0002. Water, 1.33. And so we're seeing Snell's law in action. Okay. I've got 3 examples in my overheads of propagation, reflection, refraction of light rays. So to be honest with you, I've never got through these 3. I can only get through 2. So I will try to get through 3, but we might just get through 2. But they are just good examples of propagation, reflection, and refraction. So these are how we practice, how we get to be friends with the laws of propagation, reflection, and refraction. Oh, but I've got a quiz first. Just one more reason I won't get to. Oh, that was pretty good timing. So I'll give you a moment to think about this, but not much more than a moment to think about this because I'm panicked. We've got light traveling from one medium to another medium, from medium 1 on the left to medium 2 on the right. The light rays incoming and outgoing are pictured. From that picture, can we tell whether material 1 or material 2 has a larger or smaller refractive index? Or maybe they're the same. Can we make that decision just based on the ray tracing, just based on the rays, the picture alone? Okay, I'm going to move on. Can we determine which material has larger or smaller refractive index? In the words of Bob the Builder, yes, we can. The light ray we see is bent towards the normal. The incident angle is bigger. The refractive angle is bigger. We said that Snell's law, which relates the angles to the refractive indices, says that the refracted angle is going to be smaller. You're bent towards the normal if NR, the index of refraction of the material that you're heading into, is larger. And so we know from the picture, because we're bent towards the normal, that the incident material has a smaller refractive index, the outgoing material, the refractive material, has the larger refracted index. So we can answer that. And so that's, which one is that? Medium 2 has the larger refractive index than medium 1. Okay. So this is going to be an example of law of reflection, and then I've got an example of law of refraction. And the example of law of reflection involves an instrument that we've learnt to build understanding the nature of reflection, the law of reflection. And it's called a retroreflector, and it's actually a very important instrument. A retroreflector is an arrangement of mirrors. And it's an arrangement of mirrors such that if you shine a light ray at the mirror, then that light ray is sent back exactly along its path. Comes back exactly 180 degrees to the direction it was originally heading. And it doesn't matter whether, supposing that the mirror is right here. Send a light ray, comes back straight down this path. Well, it didn't sound exciting. But now supposing I go over here and I point the light beam also at the mirror, and it still comes back along the same path. That sounds weird. How's that possible? And I go over here and I point the light ray at the mirror that's now over there, and it still comes back along the same path. That's what a retroreflector does. No matter where you shine light at it from, it always sends the light ray back along the path it arrived at. It always deflects the light ray by 180 degrees, returning it where it came from. These are not suitcases. So these are retroreflectors that were taken to the moon. And they were left on the moon so that we could point a light beam at the retroreflector on the moon, and we would get the light beam bounce back to us. So if we were in a lab, and I'm in the lab, I'm pointing my light beam, my laser beam, at the retroreflector on the moon, the retroreflector on the moon will direct that light ray straight back to me, and so I'll be able to measure it. And what's fantastic about this, I can time how long it took to get to the moon. Now, how long it took to get to the moon and then get back to me depends on, well, it depends on the speed of light. We know the speed of light depends on how far away the moon is. We can measure how far away the moon is. And so they left the retroreflectors on the moon. We've been measuring how far away the moon is over the last, 50 years or whatever it is. And what have we found out? The moon's actually getting farther away from us. I don't know if you know this, and I thought about not telling you, but the moon each year is getting further away from us. Now, it's only getting further away from us by a small amount, a few centimeters every year, but the moon is getting further away from us, and we've measured it with a retroreflector, which is an instrument that we built that was based on our understanding of the law of reflection, which is based on, ultimately, the fact that there is a dimension in nature which has positive and negative charges. So it's a whole amazing story to measuring the distance to the moon and finding it's falling away from us based on there being plus and minus charges, and that being a property of nature. Okay. So how does it work? We'll see how it works. So I'm going to sort of imagine a two-dimensional version of a retroreflector. It's actually a three-dimensional object, but we'll imagine it a two-dimensional version in a two-dimensional world. Here's the retroreflector. It comprises the two-dimensional version, two mirrors that are at right angles to one another, 90 degrees one another. So one's horizontal and one's vertical. You shine a light ray in, it's going to bounce off the first mirror, but then it's going to bounce off the second mirror and head out. And you notice here I've drawn the outgoing light ray heading out at 180 degrees in the same direction that the light ray came in at. And no matter what angle I come in at, whether it's a steeper angle or a shallower angle into this retroreflector, the light ray, the amazing thing about the retroreflector, it's always going to direct the light back along the path it arrived from. And so that's how we can shine light on the retroreflector on the moon and get the light ray back into our lab. So how does this work? It's all based on the law of reflection. All based on understanding the law of reflection and the two reflections that occur here. So let's walk through it. So this is just a diagram. So I've got a bunch of slides here where I just keep adding little bits. So I wanted to pretend I make a lot of slides for a class, so I just made the same slide, repeated it over and over, and added a little bit each time. Here's the retroreflector again, horizontal mirror, vertical mirror. Here's the incoming light ray. Here's the outgoing light ray. There's a reflection downstairs here off the horizontal mirror that obeys the law of reflection. There's a reflection upstairs here off the vertical mirror that obeys the law of reflection. I've denoted the incident angle and the outgoing angle, incident and reflected angle, downstairs here by just thetas, and they're the same. That's the law of reflection. I've denoted the incident angle and reflected angle on the vertical mirror as theta primes. And again, they're both the same. So the law of reflection is that these two thetas are the same thetas. These two theta primes are the same theta primes. But this is just the geometry. I'm just telling you my language for describing the geometry here. What we really want to know is the total deflection of this light ray that's heading upwards upstairs here to the left, based on the direction it arrived from, which was also from the left and upstairs here. So how much did the light ray get turned around? How much did it get deflected? The way we're going to figure that out is by figuring out this deflection downstairs here, which is the first deflection that occurs at this first reflection. The second deflection over here, which is on the vertical mirror, this is a second bending, turning around of the light ray. We're going to figure out these two deflections. I called them delta, that's D, Greek D, delta 1, delta 2 for the first deflection, second deflection. I'm going to figure out delta 1 and delta 2, and then I'm going to add them together to get the total deflection, and that's going to be how the retroreflector works. Okay, so what is the reflection? What is the deflection down here of the bottom mirror? Well, this dashed line here, this grey dashed line here is the direction that the light ray would travel if the mirror wasn't there. So that's the undeflected direction. So we want to know the angle from the undeflected to the true deflected angle. So we want to know this angle in red here. How big is it? Well, this is where high school, you'd be pleased to know, high school geometry comes in useful. This angle here, the delta 1, is 180 degrees, this whole half a circle here, less this theta, less this theta. So the deflection here is the remainder from 180 degrees after subtracting off the incident angle and the refracted angle. And you can see it clearly on the diagram. Here's 180 degrees, this whole semicircle. We've lost this theta I, this theta. We've lost this theta. What remains is the 180 degrees minus the 2 thetas. Hope everybody's okay with that. What's the deflection upstairs here? It's entirely the same argument, right? Here comes the incident ray. The dashed grey line is the direction it will go in if it was undeflected. What is its actual deflection as it travels upstairs here towards the top left? Its actual deflection in red here, we called it delta 2, is the 180 degrees around this complete half circle here, less this angle, theta prime, and this angle here, theta prime. So it's 180 degrees minus 2 theta prime. So that's just, there's nothing about law of reflection in what I really did there. It's just about a bit of geometry. That half a circle is 180 degrees. And we just subtracted a couple of angles from a half of 80 degrees for the 2 reflections. And so now what we've got to do is just add theta 1 and theta 2, delta 1 and delta 2 together to get the total deflection. Before we do that, I want to point out one more bit of geometry. So we used a bit of geometry to calculate delta 1, calculate delta 2 from theta and theta prime. But another bit of geometry that's hidden in the figure is that theta and theta prime are actually related to one another. They're connected to one another by geometry of a right angle triangle. See, we've got a right angle triangle in our picture. There's various ways you can draw it, but I drew it in yellow here. Here's a right angle triangle. So here's the right angle between this horizontal and this vertical. That's the right angle in the right angle triangle. The angle downstairs here is this law of this theta I or theta R for the first reflection. So that's the theta. And this angle up here is the incident or reflected angle for the second reflection. That's the theta prime. And so there's a right angle triangle that's hidden inside our sketch that has a right angle, and then the other 2 angles are the theta and the theta prime. And we know the sum of the 3 angles, the right angle, 90 degrees, and the theta prime, must add up to the 180 degrees that every triangle has. And so it must be that theta and theta prime, what do they add up to? They have to add up to 90 degrees. Because if we add the 90 degrees to the other 90 degrees here, we get the 180 degrees of every single triangle in the world. Okay, so we know here another bit of geometry that theta and theta prime sum to 90 degrees. Okay, so that's all the geometry lesson for this particular problem. We've calculated delta 1, delta 2, the 2 deflections, and we know that in those 2 deflections there's thetas and theta primes. We know that thetas and theta primes are related. Let's put that all together. The total deflection of the light ray is the sum of the 2 deflections. So delta equals delta 1 plus delta 2. The first deflection was 180 degrees minus 2 theta, the incident and reflected angle, the first deflection. The second one was 180 degrees minus 2 theta prime, the incident and reflected angles for the second reflection. Let's rearrange this equation. Let's just rearrange this with a little bit of algebra. I add the 2 180s together, 360. And I'll combine the 2 theta and the 2 theta prime with the common factor 2. I get 2 times theta plus theta prime. But theta plus theta prime is 90 degrees. So this is 2 times 90 degrees, which is 180 degrees. So we got 360 minus 180 degrees, which is 180 degrees. So we found out the light ray gets deflected back in the direction it came from. So I don't know who invented the retroreflector, but somebody realized that if you make this arrangement, this is a 2-dimensional arrangement, but you can make a 3-dimensional arrangement. You can always reflect a light ray back in the direction it came from. And that's a very useful thing. If you're a surveyor, right, that's a pretty useful thing. And if we're surveying the distance to the moon, that's a pretty useful thing, and we've used it. Okay. That was example of reflection. Now example of refraction. This is a picture. I actually don't know whether this picture is the moon or the sun in the sky. But it's either the moon or the sun in the sky. And you know, the sun is very bright. We wouldn't look at that. The moon is you know, not so bright. We can look at that. And so here is the moon or the sun. Maybe you've noticed, or maybe you haven't, that sometimes when you look at the moon, hopefully not the sun, you not only see the moon or the sun, but surrounding the moon or the sun is actually often, or sometimes, frequently, a halo. The moon has a halo, and the sun has a halo around it, and you can see that in this picture. It's not that bright, but it's quite clear. Here's the halo. You can see it most clearly downstairs here, right? This bright region here. But there's a circular halo around the moon or the sun in the sky. That circular halo, where does it come from? Well, the sun or the moon here is where you're seeing the moon or the sunlight directly. It's going straight into your eye. The halo arises by the sunlight or the moonlight not going straight into your eye, but rather it goes into the atmosphere and it gets refracted or bent off ice crystals, little ice prisms, little ice crystals that are in the atmosphere. So way up in the atmosphere, there's always little ice crystals somewhere, and they refract. Light travels into them and out of them, which is refraction. They refract the sunlight or the moonlight, and this 22-degree halo is located at 22 degrees away from the center of the sun or the center of the moon. Is due to that refraction. And so this is a feature that retroreflectors was a man-made thing, that we tamed light and using light. This is a natural phenomenon that you can observe, this halo around the moon and the sun, that we understand now based on the law of refraction. Okay, so can we explain this halo? And the answer is that we can explain this halo. This halo arises because of refraction of light when it travels into and out of a light crystal, and the 22 degrees angle of the halo is related to the minimum amount, the smallest amount that light is refracted or bent when it travels through an ice crystal, when it travels through a little ice prism in the sky. And so we're going to try and predict the 22-degree halo. Okay, so here's a picture of how the effect arises. So as I say, the atmosphere is littered with ice crystals. All throughout the atmosphere, the upper atmosphere, is typically ice crystals. And ice crystals have a very regular arrangement. They're like little 60-degree prisms. So just imagine that this is a light crystal. Now, when light strikes the crystal, it's bent, refracted when it travels into the crystal. It's bent, refracted when it travels out of the crystal. And so you see the refraction of light here at the atmosphere ice boundary, the refraction of light here on the right at the atmosphere ice boundary. So there's two refractions going on. Now in general, the amount of deflection of the light ray that arises from the two refractions, there can be different amounts of deflections, smaller or larger deflections. But there is a smallest deflection. There's no smaller deflection than the deflection that's possessed by this light ray that I drew. This light ray that I drew is a special light ray. It travels through the crystal parallel to this surface here. And so this geometry that I pictured, this particular deflection I pictured, is the minimum deflection, and that halo occurs at the minimum deflection. The light is concentrated, tends to be concentrated with a deflection near the minimum deflection. And so that's how the halo arises. And so we're going to calculate what that minimum deflection is. Now, no smaller deflection, so inside the halo, is possible. So that's why it's darker inside the halo and lighter outside the halo. It's because refraction of ice crystals can never cause refracted angles that are deflections that are smaller than 22 degrees, can only create deflected angles due to the refractions that are greater than the 22 degrees. So that's why we get the halo. And so we're going to calculate the total deflection for this geometry here. And this is just an example, now just becomes an example of law of refraction. Here's the incident ray. There's one refraction here, second refraction over here. These two refractions called a total deflection of the light ray. It was traveling in this direction upstairs towards the right. It's now traveling in this direction downstairs towards the right. What is the deflected angle? How much angular change was there? Change in angle when it traversed the crystal. So we want to find out this angle I call delta again, the deflection, the Greek d, delta. Okay. So what I'm going to do is I'm going to calculate the deflection due to the refraction on the left side of the crystal. So I have a few slides like last time where I just walk through how to calculate the deflection at this left-hand side. I called that delta L. There's a the same deflection actually occurs on this side. On the right-hand side. There'd be a similar, the same deflection, delta R, on the right-hand side. And I won't calculate that because the calculation is exactly the same as calculating the left-hand deflection. So we'll just do one of the two and note that kind of because of the symmetry of this arrangement, those two deflections are the same. So I'm just going to actually calculate delta L, and then I'm going to double it. Okay, so to begin with, this slide just defines the relevant angles. Here's the incident angle at this incident surface. It's measured with respect to the normal. So this is theta I. This theta R here is the refracted angle. And you see it's bent towards the normal because it's traveling towards from lower refractive index to higher refractive index. So this is the theta R. So those are the two angles that are in Snell's law, theta I and theta R of Snell's law, related by the two refractive indices that go in Snell's law. And this is the deflection. This was the original direction. This is the new direction. The angle between them is the deflection. That's the delta L. Just a little bit of geometry to get us. This is like a warm-up. If I was to ever go and exercise, you're meant to do a warm-up. Apparently, this is the warm-up. 60 degrees. This angle here is also 60 degrees between this horizontal light ray and this surface here. So we know this angle. That's because we said we're considering a light ray that runs horizontal, runs parallel to this surface. This bottom surface is 60 degrees to this edge. And so this similarly horizontal surface must be 60 degrees to that edge also. So we know this angle is 60 degrees. Just a little bit of geometry there. If that's 60 degrees, and this is the normal, this red line is the normal, 90 degrees to that surface, if this is 60, this must be 30. because the two of them have got to add up to 90. So maybe we didn't first think of it, but we're almost told what the refracted angle is. We can quickly see that the refracted angle must be 30 degrees, because if we add it to 60 degrees, we've got to make 90 degrees. And so we know the refracted angle. So that's a big step. If we know the refracted angle, and we know we've got air and ice, and we know the refractive indices of air and ice, we can calculate the incident angle. So let's calculate the incident angle next with the law of refraction. Here it is. Snell's law says that the incident angle, so this theta I, and the refracted angle, this theta R, are related to one another through this little equation here, where Ni and Nr are the two refractive indices. Ni, that's the refractive index of the air, that's essentially 1. We'll just use 1. It's 1.00029, but it's 1. And R, that's the refractive index of the ice, if you remember from that table, is 1.31. And so we're going to use 1.31 as the refractive index of this material here. So I took Snell's law, I plugged in Ni being 1. So just got a 1 here. I plugged in Nr being 1.31, that's for the ice. And I plugged in the fact that I know the refracted angle is 30 degrees. The only thing I don't know in Snell's law is the incident angle. So I can solve this little equation here for the incident angle by finding first the sine of the incident angle, then the incident angle itself by inverse sine. I get 40.9 degrees. So this is just applying Snell's law. And so the incident angle is 40.9 degrees. Look, just to check it, we're going from lower to higher refractive index, so we're going to be bent towards the normal. We came in at almost 41 degrees, we're bent towards the normal, we go out at 30 degrees, so we are bent towards the normal. And the amount of bending was determined by Snell's law. Okay, so now we've got the incident angle, the refracted angle. We're almost there. If we want the deflection, well, the deflection is just the difference between these two angles, right? The undeflected ray would be this direction here. It's 40.9 degrees above the normal, like this incident ray is 40.9 degrees below the normal. So if I was to specify the undeflected direction, it would be 40.9 degrees above the horizontal, above the red line, above the normal. Now, the actual reflected ray is not 40.9 degrees above the normal, but rather it's just 30. So the ray has been deflected by 10.9 degrees, the difference between 40.9 and 30. That's the deflection of the ray. So we've got almost 11 degrees of deflection here. And so that's the deflection at the left-hand surface. As I say, the calculation for the deflection on the other side of the ice crystal, so over here, that procedure is exactly the same. It's just this combination of a little bit of geometry, Snell's law, to solve for what is the deflection over here. And it is also delta right, the right-hand deflection is also 10.9 degrees. So I'm not going to go through it because it's exactly the same calculation. Is everybody okay with this? So we got, this is just me showing you. I spent all that time saying I'm not going to calculate it, but I actually did calculate, and it was 10.9 degrees. But here's how I calculated, but I put it all on one slide just for reference. And these are all the steps just for reference. So we got 10.9 degree deflection here on the left. We got 10.9 degree deflection here on the right. What's the total deflection? It's 10.9 plus 10.9 is 21.8 degrees, almost 22 degrees. What was the halo at? The halo was at 22 degrees. So that halo is literally telling us where that halo comes from. It's coming from something in the atmosphere that has a refractive index of 1.31, that under 2 refractions gives a halo at 22 degrees. We know that ice has that refractive index. So we're able to determine that there's ice in the atmosphere by the angle of the halo. If there was, crystals of diamond in the atmosphere, then the halo would be at a different angle. We'd be able to determine it is crystals of diamonds in the atmosphere because of the different angle of the halo. Anyway, those are two examples of the laws of propagation, reflection, and refraction of light. There's one more example about sunset and sunrise in my slides. I'd encourage you to take a look at that. It's also about law of refraction and propagation of light. Next class, in the following class, we're going to start talking about lenses and mirrors and microscopes and telescopes and all the things that we've done with technology by understanding the nature of light.